Welcome to Science Pills. I mean, imagine looking at a photograph of a kindergarten classroom.
Okay, I'm picturing it.
Right. So you see a bunch of toddlers sitting on a rug playing with blocks. But right there, in the middle of the group, sitting cross-legged, is a 40-year-old man in a tailored suit.
Just completely out of place.
Exactly. He's checking his watch, clearly stressed about his mortgage. You would immediately think the photo was a fake,
Oh,
or...
absolutely.
Yeah.
It makes no sense for him to be there.
Well, we are taking you into a story today where the James Webb Space Telescope just took a picture of the baby universe, and we are finding exactly that. Millions of them.
Yeah, and it is arguably one of the most profound structural crises we've faced in modern astrophysics. I mean, we built this telescope to look at the dawn of time, expecting to find them messy, fragile beginnings of galaxies.
Right, the toddlers.
Exactly. But instead, we're finding fully formed monsters.
And that is exactly why we are bringing you this custom-tailored shortcut today. We're looking at one of the most fiercely debated mysteries in space science right now. Astronomers are calling them little red dots, or LRDs.
Right, which sounds harmless, but they're anything but.
Yeah, they're these tiny, impossibly brilliant pinpoints of light. And our mission in this deep dive is to sift through a massive stack of fresh research. We've got papers from 2024 to 2026, JWST Cycle 5 proposals, and deep dive analyses.
A lot of reading.
A ton of reading. And the goal is to figure out what they actually are. Like, are they ultra-dense clusters of stars? Are they hidden supermassive black holes? Or are they a completely new classification of celestial object?
Like something out of a sci-fi novel.
Right, like a black hole star. So to really grasp why the scientific community is so riled up, you have to understand the specific timeline we are looking at here.
Yeah, the timeline is everything. JWST is basically a time machine. Because light takes time to travel, when it uses its near-infrared sensors to look at the deepest patches of space, it's seeing light that left its source over 13 billion years ago.
Which is just staggering to think about.
It really is. We're looking at redshifts greater than 5, which corresponds to the first 500 million to maybe 1 billion years after the Big Bang.
The Stone Age of the cosmos.
Precisely.
To use another analogy, it's like archaeologists meticulously brushing away dirt in a layer of earth from the Paleolithic era. They expect to find flint arrowheads and maybe some charred bones.
Right.
But instead, their shovels clink against the steel and glass roof of a fully constructed 100-story modern skyscraper. It challenges our entire timeline of how things are built and, what materials were even available back then.
That's a great way to put it, because the standard model of cosmology, the lambda CDM model, it dictates that the universe operates on a bottom-up schedule.
Bottom-up meaning small things merge to make bigger things.
Exactly.
Yeah.
After the Big Bang, you have dark matter and dark energy dictating the expansion. Gravity is a very weak force, so it takes hundreds of millions of years for cold, dark matter to slowly pull primordial hydrogen gas into clumps.
And then those clumps ignite.
Right, they ignite into the first stars, and then those stars slowly merge into dwarf galaxies. Building a massive galaxy should take billions of years.
But then JWST boots up, and it runs these massive early operation sky surveys.
Projects with acronyms like SEERS, Uncover, Rubies, and Jades.
Yeah, those ones. And it starts spitting out images of these little red dots, and they aren't just like one or two flukes, are they?
Not at all. The papers show they account for about 1% of all known galaxies in that first billion years.
1% doesn't sound like a lot, but on a cosmic scale.
It's huge. To put a finer point on it, the data reveals a surprisingly high co-moving number density. We are looking at about 10 to the negative 5 per cubic co-moving megaparsec.
Okay, let's translate that for the listener. What exactly is a co-moving megaparsec, and why does that specific number matter so much?
Good question. Think of the universe as a giant expanding sandbox. A co-moving volume is just a way of measuring a chunk of that sandbox that expands along with the universe.
So it scales up as the universe stretches.
Exactly. It allows us to compare how crowded a specific patch of space was 13 billion years ago to how crowded it is today without the expansion of the universe throwing off our math.
Got it.
So finding an abundance of 10 to the negative 5 at that early stage, it means there are 10 times more of these objects than our extrapolations of the early universe predicted.
It's 10 times more.
They are everywhere.
So they are ubiquitous. But let's talk about what they actually look like, because the physical profile of a little red dot is where things get really, really weird.
Yes, the morphology.
Right. There are two main traits here. Trait number one is extreme compactness. Even with JWST's near-infrared camera in our CAM, which has unprecedented resolution, these things appear as unresolved point sources.
Meaning they don't have shape.
Exactly. They aren't blurry, sprawling spirals. They are tight little pinpoints with physical radii often smaller than 100 parsecs.
To give you a sense of scale on that, the stellar disk of our Milky Way galaxy is roughly 30,000 parsecs across.
Wow. Okay.
These objects are cramming an immense, blinding amount of energy into a space less than 100 parsecs wide. That is smaller than a single typical star cluster in our own galaxy.
Which is insane. And then we get to trait number 2, which is the real puzzle here, the V-shaped spectrum.
The famous V-shape.
Right. If you measure the light they emit and plot it on a graph, it forms a literal V-shape. They have this incredibly bright blue continuum in the rest frame ultraviolet, but simultaneously they have a very, very red rest frame optical color. The dip in the light, the bottom of the V, happens right around 3,500 angstroms.
And in astrophysics, seeing something intensely blue and intensely red at the exact same time is deeply contradictory.
Why is that?
Well, blue light usually means a massive burst of young, super hot stars burning through their fuel incredibly fast. Red light usually implies something entirely different.
Like what?
It means either an incredibly old, cool population of stars, which shouldn't exist in the baby universe, or it means the object is wrapped in a thick blanket of cosmic dust.
Ah, so the dust absorbs the blue light.
Exactly. It absorbs the blue and only lets the longer, redder wavelengths pass through.
It's like looking at a stereo equalizer where the bass is cranked to maximum, the treble is cranked to maximum, but the mid-range is completely muted. It just shouldn't happen naturally.
No, it shouldn't.
And this extreme redness is what triggered all those universe-breaker headlines we saw a couple of years ago, right?
Yes. When those initial papers hit, the logic was straightforward but terrifying for theorists. If that intense red light is starlight, then these little red dots must contain an unimaginable number of old stars.
Meaning they formed way too fast.
Right. Early estimates suggested we were looking at galaxies more massive than the Milky Way, fully formed, existing just 500 million years after the Big Bang.
Which completely shatters the lambda CDM model. There physically was not enough time for gravity to do that kind of heavy lifting.
Precisely.
But wait, I have to push back here. Whenever I see a viral headline claiming the Big Bang is broken, isn't it much more likely we are just misinterpreting the light we're seeing? Like maybe it's not a trillion stars.
That is exactly the lifeline the astrophysical community grabbed onto. If you assume the light is coming from a brilliant accretion disk around a growing black hole, rather than from a massive galaxy of stars, the mass requirement drops drastically.
Oh, because a black hole is just so much brighter per unit of mass.
Exactly. A single feeding black hole can outshine 1 billion stars. So if these are obscured active galactic nuclei, or AGNs, then the Big Bang is safe.
Okay, so the universe isn't broken. Phew.
Not broken, just very confusing.
Right. But that just opens the door to a whole new brutal debate. The sources detail a massive schism in the community trying to explain that V-shaped spectrum and the extreme compactness.
Yeah, it's basically two camps right now.
Right. We have the starburst camp and we have the black hole or AGN camp. Let's start with the stars. If I'm reading the Baggin et al. Study correctly, they argue we shouldn't jump to black holes at all.
That's right.
They think these are purely ultra-compact, massive galaxies. The blue light is a burst of new stars, and the red light is an older, incredibly dense population.
That is their model, yes. But if they're just stars, we run into a severe physics problem.
Okay, lay it on me.
To produce the luminosity we are observing from a space smaller than 100 parsecs, the stellar mass density would have to be staggering. We're talking up to 100 billion solar masses packed into that tiny radius.
Wait, 100 billion suns in a space smaller than our local stellar neighborhood?
Yes.
What does that even look like physically? I mean, how is that possible?
It looks like chaos. At that density, the gravitational dynamics are violently unstable. The stars are practically rubbing against each other.
Wow.
Calculations show that in a cluster that dense, stars would physically collide on a near-monthly basis.
A star collision every month. That's a cosmic demolition derby. But wait, wouldn't two massive stars slamming into each other produce a very specific signature?
Exactly. And that's the fatal flaw. When stars collide at those velocities, they generate immense shock waves that superheat the surrounding gas. That superheated gas emits a staggering amount of X-rays.
Okay.
Here's where the pure stellar model hits a brick wall. When astronomers point our best X-ray observatories, like the Chandra X-ray Observatory, at these little red dots.
Let me guess. Nothing.
We see nothing. They're entirely X-ray quiet.
So it literally can't be stars. The math just breaks down.
It falls apart entirely.
Okay, so we default to the other camp, the active galactic nucleus, or AGN, model. The idea is that these are supermassive black holes. The blue UV light is coming from the outer, unattenuated part of the accretion disk, and the red optical light is the inner part of the AGN, heavily obscured by dust.
It sounds like a really neat solution on paper.
But there's a but.
A huge but. The AGN model faces an equally devastating hurdle. A feeding supermassive black hole doesn't just emit optical and UV light. The friction in the inner accretion disk gets so intense that it creates a blindingly hot corona of plasma.
Which should produce X-rays.
Right. The corona should scream in X-rays. Furthermore, the magnetic fields twisting around the black hole should launch powerful jets of particles that emit bright radio waves.
But just like with the star collisions, there are no X-rays, and let me guess, no radio waves either.
None whatsoever. Astronomers use a technique called deep stacking.
What's that?
They take X-ray and radio observations of hundreds of these individual little red dots, which individually might be too faint to read, and they digitally overlay them.
Ah, so they stack them to amplify the signal.
Exactly. If there was even a faint, consistent signal across the population, stacking hundreds of them would amplify it and reveal it. But the stacked images are flat.
Just flat.
Completely flat.
Yeah.
They're completely quiet in both X-rays and radio frequencies.
So if it's a black hole, it's a black hole that's somehow hiding its most defining characteristics. That's so strange. But I was reading that piece from the CERN Courier in our stack, and they pointed out an even bigger flaw with the AGN model. It's the dust problem.
Yes, the conservation of energy.
Right. If we assume thick cosmic dust is making the black hole look red by blocking the blue light, we run into the absolute most fundamental law of physics. Energy cannot be destroyed.
Exactly. If you have a brilliant superluminous accretion disk blasting out high-energy UV photons, and you wrap it in a thick blanket of dust, those photons don't just vanish.
The dust has to absorb them.
Right. The dust grains absorb the UV radiation. And when dust absorbs intense radiation, it heats up.
And hot things have to glow?
Precisely. In the vacuum of space, heated dust glows intensely in the far infrared spectrum. If the dust model were correct, these little red dots should be absolute beacons in the far infrared.
That they aren't, are they?
Not at all. When astronomers pointed the ALMA radio telescope array and Webb's MIRI instrument, both of which are exquisitely sensitive to far infrared dust emission, they found a total, baffling lack of far infrared light.
Wow.
So the dust model is functionally ruled out.
Man, so it's like we are looking at a massive raging bonfire from a distance. We can see the intense light, but there is absolutely zero smoke in the air, and when we look at it with a thermal camera, there is zero heat signature.
That's a perfect analogy.
It defies basic thermodynamics. No X-rays, no radio, no heat. So, I mean, how do we fix the math? What's going on here?
We have to completely rethink what is happening to the light before it reaches our telescopes. And that brings us to a revolutionary paper published in 2026 by Rusakov and his team.
Okay, let's get into Rusakov.
They decided to stop looking at the overall brightness and start looking at the specific shape of the light waves, specifically the Balmer emission lines.
Okay, let's unpack Balmer lines, because this seems to be the key to the whole mystery.
It is.
So think of a spectrum of light like a piano keyboard. A Balmer line is essentially a single, very specific note, a specific wavelength of light emitted when an electron in a hydrogen atom drops from a higher energy state to a lower one.
That's a great way to visualize it.
Usually it looks like a sharp spike on a graph, but in little red dots, these lines are broad. The spike looks smeared out into a wide mound. Why is that important?
Well, for decades, the standard astrophysical interpretation of a broad emission line has been Doppler broadening.
Like a Doppler effect with an ambulance siren.
Exactly. If you have a cloud of hydrogen gas swirling around a supermassive black hole at millions of miles per hour, some of that gas is moving incredibly fast toward you.
And that compresses the light.
Right? Shifting its wavelength to the blue end. Meanwhile, the gas on the other side of the black hole is moving incredibly fast away from you, stretching its light toward the red end.
So the sharp spike of the Balmer line gets stretched in both directions, making it look broad on the graph.
Yes. And astronomers use the width of that broad line to calculate how fast the gas is swirling.
Right, and from the speed of the gas, you can use basic Newtonian physics to calculate the gravitational mass of the black hole required to whip the gas around that fast.
That's the standard practice. And when they ran this standard calculation on the broad lines of little red dots, the math said These black holes must be enormous.
Like how big?
Somewhere between 10 to the 8 and 10 to the 9 solar masses. Hundreds of millions to a billion times the mass of our sun.
But Ruskov's team looked closer, didn't they?
They did. They analyzed the core of that broad line. And what they found flips everything upside down. They realized it wasn't Doppler broadening at all. The gas isn't swirling at millions of miles per hour. The lines are actually being broadened by a completely different mechanism called electron scattering.
Electron scattering. Okay, what is that?
This is a phenomenal piece of detective work. Electron scattering happens when the source of the light is buried inside a phenomenally dense cloud of free electrons, a highly ionized plasma.
Okay.
As the photons of light from the hydrogen emission try to escape this dense plasma, they act like pinballs, constantly bouncing and ricocheting off the free electrons.
So every time a photon bounces, it gains or loses a tiny random fraction of energy.
Correct. By the time those photons finally fight their way out of the plasma cloud and travel 13 billion years to our telescope, their energies have been entirely randomized and smeared out.
That's wild.
They look broad, but it has absolutely nothing to do with the gravity or the speed of the gas.
This is an incredible aha moment. So it's like looking at a street lamp through an incredibly thick, swirling fog. The glow looks massive and dispersed, making you think the bulb inside must be huge and incredibly powerful. But the fog is just scattering the light. By mathematically stripping away the fog of electron scattering, Rusikov's team realized the actual bulb inside is tiny.
And the implications for the mass of these objects are staggering because the intrinsic lines of light before it hit the electron fog are actually quite narrow. The gas is moving much slower than we thought.
Which means the mass is drastically lower.
Right. It means the central black hole is much weaker. The mass estimates plummeted from 1 billion solar masses down to roughly 10 to the 5 to 10 to the 7 solar masses.
Wow.
A reduction of 2 whole orders of magnitude.
We shrunk the black holes by a factor of 100. So they aren't impossible giants breaking the universe. But wait, does this electron fog also solve the other mysteries? Like the missing X-rays, the missing dust heat?
It solves them perfectly. It's a beautifully elegant physical model.
I have so.
The electron scattering proves that these black holes are cocooned in extremely dense, optically thick ionized gas. Not dust.
Go.
Gas. This dense gas cocoon acts as an impenetrable shield. When the black hole's corona generates X-rays, they hit the dense gas and are immediately absorbed and thermalized.
Oh, I see.
When the magnetic jets try to emit radio waves, the plasma suppresses them through a process called free absorption.
The signals are being produced, but they are trapped. They literally can't punch through the fog.
Exactly.
And because the cocoon is made of ionized gas and not dust, it doesn't heat up and glow in the far infrared.
Right. It just absorbs the extreme UV energy, puffs up, and re-radiates that energy as the cooler red optical light we see.
Creating that distinct V shape.
You got it.
Man, that is so satisfying. It paints a picture of a transient, wildly chaotic early phase of black hole evolution that we simply hadn't recognized before.
Yeah, these are young, relatively low-mass AGNs accreting matter at or near what we call the Eddington limit.
Which means they're feeding incredibly fast.
Feeding so fast that the outward pressure of their own radiation is barely held in check by gravity.
Okay, so we stripped away the illusions and we have this powerful new framework of a black hole wrapped in a dense gas cocoon. But to really understand how wild this gets, we need to look at the extremes.
Right, the specific cases.
Yeah, the research details 2 specific, highly detailed case studies to ground the science. Let's look at the first one, J1007 AGN, which was detailed in a 2025 paper by Schindler and his team.
J1007 is a spectacular find. It was discovered at a redshift of 7.3.
Okay.
Even under our new reduced mass calculations, it is an absolute powerhouse. It has an intrinsic bolometric luminosity of 10 to the 46.6 ergs per second.
Okay, an erg is a unit of energy, but 10 to the 46.6 is just noise to a human brain. Let's ground that.
Yeah.
If you took the total amount of energy our sun will produce in its entire 10 billion year lifespan, J1007 burns through that much energy in just a few hours.
That's a staggering comparison.
Oh.
But it's accurate. It is absurdly bright.
It is, and it hosts a central black hole of about 500 million solar masses, making it one of the larger objects in this class. But the luminosity and the mass aren't even the most vital details here. Right?
No, they aren't. The crucial discovery Schindler's team made is about J1007's neighborhood.
Right.
They found that it is embedded in a massive overdensity of 8 nearby galaxies.
It's clumped together with a bunch of neighbors.
Exactly. And by analyzing this cluster, astronomers could calculate a statistical measure of its environment called the cross-correlation length. For J1007, the length is 8 plus or minus 2 inverse little h co-moving megaparsecs.
Okay, let's translate cross-correlation length for the listener. Essentially, this is a mathematical way of measuring how clumpy the universe is, right?
Yes.
It tells us how likely we are to find one of these objects near other galaxies compared to just throwing a dart at a totally random empty patch of space.
That's exactly it. And a cross-correlation length of 8 is exceptionally high. It tells us that J1007 resides in an incredibly massive deep gravity, well, a giant dark matter halo.
Okay.
What is truly fascinating here is that this specific level of clustering is directly comparable to the clustering of highly luminous unobscured quasars at similar redshifts.
Unobscured quasars being the incredibly bright, naked, supermassive black holes we already knew existed back then.
Correct. But here is the kicker. Based on this clustering data, cosmological models suggest that nearly all dark matter halos above a certain mass threshold, specifically those above 10 to the 12 solar masses at that era, must host actively accreting black holes.
Wait, you're saying all of the giant dark matter halos have one of these inside them?
Nearly all of them. And this is a massive paradigm shift. Traditional luminous quasars are rare. They only seem to be on or feeding less than 1% of the time.
Right.
But J1007 suggests that little red dots are not weird anomalies.
Yeah.
They might be the mandatory obscured precursor phase to bright quasars.
Ah.
Every giant naked quasar we see later in cosmic history might have started its life wrapped in one of these dense gas cocoons, appearing to us as a little red dot.
That is mind-blowing. It's like finding a strange glowing chrysalis in the jungle and then realizing that every single giant butterfly in the sky had to go through that exact hidden stage. It connects the timeline perfectly.
It really does. It ties the whole picture together.
Okay, so J1007 gives us the big picture of how they fit into galactic evolution. Now let's look at our second case study, which is just an absolute freak of nature. They call it the cliff.
The cliff, officially designated Ruby E's UDS 154183, is a phenomenal object.
A bit of a mouthful, though.
Yeah, the cliff is much better. It is located at a redshift of 3.55, meaning we were seeing light from about 11.9 billion years ago. And it gets its nickname from a very specific feature in its spectrum, an exceptional Balmer break.
We talked about Balmer lines earlier, which are emission spikes. What physically is a Balmer break?
A Balmer break is a sharp, sudden drop-off in the continuous spectrum of an object's light, occurring right around the 3646 angstrom mark.
Okay.
In traditional astronomy, a strong Balmer break is the ultimate undeniable signature of an older, evolved stellar population.
Why do old stars cause a drop-off like that?
Because as stars age and cool down, their atmospheres become perfectly tuned to absorb light at wavelengths shorter than the Balmer limit. The atmosphere of an old star acts like a physical filter, blocking the higher energy light.
Oh, I see.
So when you look at a cluster of old stars, you see a steep cliff in their light emission.
So the cliff has a drop-off in its light that is so steep, so drastic, they named the whole object after it. The research notes the break is twice as strong as any high redshift source previously observed.
It's extreme.
So if a Balmer break means old stars, doesn't that prove the starburst camp was right all along? Like maybe it is just a massive clump of dying red dwarfs.
You would certainly think so. But the math completely breaks down if you try to build that model.
How so?
Researchers from the Ruby-C's team desperately tried to fit the cliff spectrum to a model of massive evolved stellar populations, and it failed spectacularly. They tried tweaking the parameters, introducing radical variations in the initial mass function, basically altering the assumed ratio of large to small stars.
Right.
They tried adding unusually steep dust attenuation to fake the drop-off.
Yeah.
Nothing worked. They couldn't replicate the sheer steepness of the cliff.
And even if they could somehow force the math to work, they run right back into the density problem we talked about earlier, right?
Yes, exactly.
To produce that much light with an old stellar population, the cliff would need a stellar mass of over 10 to the 10.5 solar masses crammed into a tiny radius of about 40 parsecs.
Exactly. And the X-ray collision problem returns with a vengeance. A star cluster that dense would be an inferno of stellar collisions, screaming in X-rays.
But it's quiet.
The cliff is completely silent in the X-ray band, so it physically cannot be an ultra-dense massive galaxy.
So if J1007 tells us these things are the hidden parents of quasars, what does the cliff tell us?
The cliff is crucial because its extreme nature strips away all the ambiguities. Because the stellar model fails so undeniably here, it provides the clearest evidence to date that at least some LRDs, and likely the vast majority, are powered by a central ionizing source embedded in dense gas.
It forces the AGN gas cocoon model.
It forces us to accept it, yes, but it also introduces an even more terrifying question. If these are supermassive black holes sitting in the early universe, how on earth did they get there so fast?
And that launches us directly into the origins of these things, because standard models of black hole formation are way too slow.
Way too slow.
In the modern universe, a giant star runs out of fuel, explodes in a supernova, and leaves behind a stellar mass black hole. That black hole then spends billions of years slowly feeding on gas and merging with other black holes to become supermassive.
That's the traditional route.
But we are looking at the universe when it was barely a toddler. There wasn't time for billions of years of feeding. We need exotic theories here. Let's explore the bleeding edge of astrophysics.
The literature presents several fascinating pathways, all attempting to explain how we bypass the slow, traditional stellar death route and fast-track the creation of massive black holes.
What's the first one?
The first, and perhaps most mind-bending, is the black hole star theory, or BH star.
A black hole star. It sounds like an oxymoron.
It does, but it beautifully addresses the bizarre spectrum of objects like the cliff. The BH star theory proposes that you have a powerful black hole, accreting matter at super Eddington rates, feeding much faster than is theoretically stable.
Okay.
But this black hole didn't form in empty space. It is deeply embedded inside an incredibly massive, dense, spherical shell of gas. The radiation from the black hole cannot escape directly.
So the intense radiation from the black hole heats up the gas shell from the inside out.
Exactly. The black hole acts as an internal furnace. The dense gas envelope absorbs all the ferocious X-rays and UV radiation, puffs up under the immense thermal pressure, and thermalizes the energy.
Wow.
The outer surface of this gas shell then radiates that energy away as much cooler red optical light.
So what you end up observing from the outside is an object that radiates essentially like a single and possibly massive star, perhaps 1,000 astronomical units wide, powered internally by a black hole instead of nuclear fusion.
That's exactly it.
It's essentially a cosmic turducken. You have a highly active, superfeeding black hole stuffed inside an incredibly dense shell of gas, masquerading to our telescopes as a single, giant red star.
That is a perfect analogy, and it perfectly explains the strong Balmer break and the lack of UV and X-ray emission. It's all trapped inside the turducken.
I love it.
The
cosmic turducken. Okay, theory number 2 for how we get these massive engines so early. Runaway collapse in clusters. This comes from Jillian Bellaveri's 2025 paper.
Right. This model looks at the specific environments of the early universe. We know that the early cosmos formed extremely dense star clusters.
Okay.
Bellaveri theorizes that some of these clusters were so extraordinarily dense that they became vulnerable to runaway gravitational collapse. The stars were packed so tightly that they couldn't maintain stable orbits. They just started crashing into one another in a violent chain reaction.
No, instead of one star exploding, you have thousands of stars mashing together.
Precisely. These colliding stars merge rapidly to form a single, highly unstable supermassive star, which quickly collapses under its own crushing weight to leave behind an intermediate mass black hole.
Like a seed.
A seed of maybe a few thousand solar masses. But the cluster's still incredibly dense, so this new black hole seed doesn't have to slowly pull in wisps of loose gas.
What'd it do?
It feeds by continuously shredding and consuming the remaining stars in the cluster through what we call tidal disruption events, or TDEs.
A tidal disruption event, that's spaghettification, right? Where the gravity of the black hole pulls harder on the front of a star than the back, stretching it out into a long noodle of superheated plasma before swallowing it.
Exactly. The extreme friction of the star being torn apart and swirling into the black hole generates immense light and heat. In this model, the little red dot signature, the broad lines, the intense blue and red light, is being generated by the violent, continuous shredding of whole stars.
That is brutal.
It is. The high density of the cluster provides an all-you-can-eat buffet, allowing the black hole to grow incredibly rapidly, skipping the slow gas accretion phase entirely.
Okay, theory number 3, and this one requires us to talk about the invisible scaffolding of the universe. Dark matter. This is the ultralight dark matter halos theory from Buck and Lee.
This model attempts to solve the problem by looking at the very structure of gravity itself. Standard cold dark matter models sometimes struggle to explain the fine details of how early gas clumps together without fragmenting.
Okay.
Buck and Lee propose a framework involving ultralight dark matter, or ULDM. These are theoretical particles with a mass of roughly 10 to the negative 22 electron volts.
That is almost incomprehensibly light. And because they are so light, they behave differently than normal particles, right?
Yes. Because their mass is so low, their quantum mechanical wavelengths stretch to astronomical sizes. They behave more like vast waves than individual particles on a galactic scale. And one of the distinct predictions of ULDM is that at the very center of a dark matter halo, these wave-like particles condense and overlap to form a stable, ultra-dense solid-organic core.
Okay, so you have this incredibly dense knot of quantum dark matter waves at the center of a baby galaxy. What happens to the normal the hydrogen that gets pulled toward it?
The gravitational pull of that solitonic core is immense and abrupt. It strictly confines the baryonic gas, pulling it inward at terrifying speeds. The gas is squeezed so hard and so fast by the dark matter that it undergoes intense shock heating,
Raising its temperature.
raising it to above 10,000 Kelvin.
And why is that specific temperature crucial?
This is the battle between thermal pressure and gravity. Normally, when gas cools down, it loses its internal thermal pressure and gravity takes over, causing the cloud to crumble and fragment into thousands of tiny star-sized clumps.
Forming a normal galaxy.
Right. But at 10,000 Kelvin, the gas is highly turbulent. It has so much outward thermal pressure that it refuses to crumble. The dark matter core keeps the gas hot and violently prevents fragmentation.
So the cloud just keeps getting bigger and denser and hotter, but it can't break apart to form individual stars.
Exactly. Until eventually, the sheer mass of the entire contiguous gas cloud reaches a critical tipping point. The entire massive cloud undergoes direct monolithic collapse.
Ooh.
It bypasses the entire exploding star phase and collapses directly into a black hole seed of about 10 to the 5 solar masses.
So dark matter essentially forces the universe to take a shortcut. It crushes a giant cloud of hot gas straight into a heavy black hole seed.
Yes, these heavy seeds, or direct collapse black holes, provide a beautifully natural explanation for how we get to these intermediate masses so quickly after the Big Bang.
That makes a lot of sense.
Whether it's a black hole star trapping its own radiation, a runaway cluster feeding on shredded stars, or a direct collapse forced by ultralight dark matter, all these theories point to the same incredible conclusion.
Which is?
The early universe was wild, highly unstable, and it was taking aggressive shortcuts to build giant black holes.
We have all these amazing theories, but I mean, how do we prove which one is right? How do we know if it's a turducken or a dark matter shortcut? The answer is happening literally right now, isn't it?
It is.
The JWST Cycle 5 observation proposals have just been submitted, and astronomers are gearing up to turn the telescope back toward these little red dots to break the degeneracies in these models.
The Cycle 5 proposals are a testament to how fast this field is moving. We aren't waiting decades for a next-generation instrument. We're adapting our strategies in real time with the instrument we have.
Which is incredible.
For example, Takumi Tanaka's proposal is incredibly ambitious. His team is targeting an object called CWLRD Z10.
Wait, Z10, that means a redshift of 10.
Exactly. If Tanaka's team confirms this observation, it would be the first little red dot discovered at a redshift greater than 10.
That's practically right after the lights turned on.
We are talking about the very edge of the observable universe. That pushes the timeline of supermassive black hole formation even closer to the Big Bang.
What does that mean for the models?
It would place a devastatingly tight constraint on how fast these objects must grow. If confirmed, the direct collapse heavy seed models become almost a physical necessity, because there simply isn't time for anything else to happen.
Wow. Then we have proposals from Anna de Graaf and Bingji Wang. They are moving away from the near-infrared and focusing on the MRI instrument.
MAI is the mid-infrared instrument on Webb. Up until now, much of the LRD data has been in the near-infrared. But de Graaf and Wang want to look at the rest frame mid-infrared, specifically the 1 to 3 micron wavelength range.
Why is that specific wavelength range the key to all this?
Because that is where the dust versus gas debate will finally unequivocally be settled. The models predicting that the red color comes from the thermal emission of a dense hot gas cocoon make very specific testable predictions about the shape of the spectrum in that mid-infrared range.
Okay, so they're looking for a specific shape.
Furthermore, Wang's proposal is specifically looking for water absorption features.
Water. In the middle of a violently feeding black hole gas cocoon. That sounds impossible.
Yes, believe it or not. If the dense gas cocoon is thick enough, its outermost layers will be shielded from the intense radiation of the black hole.
Oh, I see.
If those outer layers are cool enough, around 4,000 Kelvin or less, molecules like water can survive without being blasted apart into individual atoms.
That is fascinating.
If MIRI detects the signature of water absorption in that 1 to 3 micron range, it proves definitively that we are looking at a cool, dense gas envelope. It is a binary test that completely rules out the old dusty AGN models.
That is brilliant, using water as a thermometer for a supermassive black hole.
Okay.
But I saved my absolute favorite proposal for last. Fengwu Sun's time delay machine. This sounds like straight-up science fiction, but it is real observational astronomy.
It is arguably one of the most elegant and creative proposals in the entire observation cycle. Sun's team is targeting a massive galaxy cluster named RxCJ2211.
Okay.
This galaxy cluster is so unbelievably massive that its collective gravity actually bends and warps the fabric of space-time around it. It acts as a colossal magnifying glass. We call this gravitational lensing.
And behind this giant cosmic magnifying glass, there happen to be 3 distinct systems of little red dots.
Yes, but because the space-time is warped, the light from those LRDs doesn't travel in a straight line to reach us. It takes multiple bending paths around the galaxy cluster.
Like a hall of mirrors.
Exactly. The result is that we don't just see one image of each LRD. We see multiple mirrored images of the exact same object smeared across the sky. Sun's team has identified 15 separate lensed images of these LRDs.
And here's the truly mind-bending part. Because each path around the cluster is a physically different length, some paths take a wider detour than others, the light from each image takes a different amount of time to reach our telescope.
Exactly. The time delays between these different images of the identical little red dots span from about 2 days to an astonishing 160 years.
Let that sink in for a second. We are looking at 15 different TV screens, all playing the exact same live feed of Little Red Dot, but each screen is on a different tape delay.
It's incredible.
We can watch the exact same black hole flicker and change across decades, even centuries, just by looking at the different mirrored images right now.
It provides a literal, functioning time machine to watch the evolution of a single object in real time.
So if we can watch the same black hole flicker across different decades through gravitational lensing, what is the smoking gun we are looking for? What proves the gas cocoon theory?
We are looking for something called spectrophotometric variability.
Meaning changes in the light over time.
Exactly. We want to see how the brightness and the shape of the broad emission lines change over time. If the BH star or dense gas cocoon models are correct, any change in the black hole's feeding rate, say a massive chunk of gas falls in and causes a flare, will ripple outward through the gas shell.
Okay.
By measuring exactly how long it takes for a flare in the blue UV light from the center to echo and cause a subsequent change in the red optical light from the outer shell, we can physically map the size, the density, and the exact geometry of the gas cocoon.
That is so clever.
It will definitively prove the structure of these objects.
That is just phenomenal. And this is exactly why this deep dive matters to you, the listener. Because we are not just recounting settled history from a dusty textbook. We are living in a golden age of astronomy.
We really are.
The rules of how the first supermassive black holes formed the very beasts that anchor galaxies like our own Milky Way, the engines that shaped the cosmos we live in, are being completely rewritten right now, in real time, based on these little red dots.
It is a profound reminder that the universe still has the capacity to completely surprise us. Every time we open a new window, like the James Webb Space Telescope, we find things that challenge our most deeply held fundamental assumptions about how physics operates on a grand scale.
Let's unpack the journey we've been on today.
Yeah.
We started with universe-breaking impossibilities, the absolute panic that the Big Bang model was wrong because these red dots appeared to be impossibly massive galaxies sitting in the baby universe.
Right, the early days of the panic.
Then we dug deeper and found the electron scattering illusions, where a microscopic pinball game in a thick fog of ionized gas was tricking our math into thinking these black holes were 100 times larger than they actually are.
A huge breakthrough.
We used thermodynamics to strip away the dust models, confirming the presence of these dense gas cocoons. And finally, we explored the wild, bleeding-edge reality of black hole stars, runaway collapsing clusters, shredding whole suns, and direct collapse heavy seeds forced into existence by the gravity of quantum dark matter.
It is a stunning arc of scientific discovery. To move from sheer confusion and panic to highly sophisticated, testable physical models in just a few short years is a testament to the incredible ingenuity of the astronomical community.
And as we wrap up, I want to leave you with a final provocative thought to mull over. If the early universe was absolutely teeming with these dense, gas-enshrouded black hole stars, these voracious seeds that eventually cleared their throats, blew away their gas shells, and became the massive, brilliant quasars that anchor our galaxies today.
What about the rest of them?
Exactly. What happens to the ones that never grew up, the ones that ran out of gas or never merged or just fizzled out? Could there be dormant, failed little red dots, naked, wandering intermediate mass black holes, completely stripped of their glowing gas shells, hiding silently in the dark corners of our own local universe right now?
That is a chilling and deeply fascinating question.
Right.
And knowing how quickly this field is moving, it's one that future surveys will undoubtedly be looking to answer.
Well, thank you for joining us on this deep dive into the little red dots. Remember to keep looking up, keep asking questions, and keep your curiosity ignited. See you next time.